Hello students, welcome to the channel Statistical Hub. This is our lecture number 9 in the course SH201A. Okay, so in this particular lecture, we are going to cover up something about generating function. So let's see what is a generating function. So if I go for the definition for the generating function, then generating function so technically you define the generating functions for different random variables. So some particular kind of generating functions, they are defined for discrete random variables only. Some are defined for all of them. Okay, so what is a generating function? So a generating function is a formal power series. It is a formal power series whose coefficients keep up some information. Keep up some information. So what kind of information? So if you go for any particular generating function, so if you just go for the expansion of that particular part, so we know this is some sort of power series. So in the power series, you will be finding different terms. So in each of the term, there will be some particular coefficient. And if you go for that particular coefficient, it will be signifying something about the distribution or something about the random variable. So that's why the generating functions, they are very important in our course of study. Okay, moving ahead with this part. So in your course or in this particular course, we have to cover different type of generating functions. So majorly, I'm going to take the first generating function, that is the probability generating function. Okay, the second thing that we have to take into consideration, that is the moment generating function. Okay, and the third one, that will be your characteristic function. And lastly, we are having the cumulant generating function. Cumulant generating function. So these are the majorly the topics that we have to cover in this particular lecture. So I will try to finish up these four different type of distribution functions. Four different type of generating functions in this particular lecture. Okay, let's try to see them one by one. So if we start with the probability generating function, so you are having PGF, that is your probability generating function. Okay, so the PGF is generally defined for, it is defined for a random variable such that this random variable is discrete plus it is non-negative. The random variable that we have to define the PGF. So we have to consider a random variable who is discrete and it is having no negative terms. Okay, so the probability generating function, that is denoted by GXS. Some books you may find PXS also, probability generating function, but I go for the GXS. Okay, so that is something expected value of S raised to the power X. Okay, now S is something that is it can be a real number, it can be some complex number, so there is nothing specified about the S. Now you can see this is something, some function of X, correct? So we are having S raised to the power X, that is some function of X. And in the last lecture, when we covered something about expectation, then we know this thing will be nothing. This will be simply summation for all the values of X. You do S raised to the power X into probability function. X is taking a particular value X. That's how we define the probability generating function. Okay, now we are having certain properties about the PGF. So we are having the properties that we have to take into consideration. So the first one, so technically the PGF is unique. It is unique for different distributions. Like two distributions, they won't be having same PGF. The second property that we are going to see is if you go for GX and if you keep 1, then that will be summation for all the values of X. We are having S, that is 1 raised to the power X, and probability function X is small x. So we can see this X random variable that will be some discrete plus non-negative. So this part will always be 1. This is summation of probabilities that will be coming out to be 1. So just remember this one thing, that if you take the S to be 1, then the probability generating function that will be taking a value 1 only. Okay, the third property that we have to take into consideration, that is something like this, that the kth factorial moment of X can be determined by differentiating the by differentiating the PGF k times and find the value at s equal to 1. So how that is coming up? So simply that is nothing. If you have to go for kth factorial moment, so we know what is the meaning of factorial. So we go for like maybe we are having x, so you do x into x minus 1, x minus 2, and so on. We have to go for the kth factorial moment. So that will be coming out like this. It will be simply expected value of x into x minus 1 and so on. We have to go for kth factorial moment. So that will be x minus k plus 1, the kth factorial moment. That will be simply you take the generating function of x at value 1 and you take the derivative for the kth time. So this is how we are going to get the kth factorial moment from the probability generating function. So this is something about the PGF that you have to take into consideration. Always remember these particular properties. Sometimes they're useful, sometimes like they are useful technically. We don't have to say like sometimes useful, sometimes not useful. Okay, let's move to the second topic. So the second kind of generating function that we have is the MGF. That is your moment generating function. Moment generating function. So as the name says, it will be used to calculate the moments. Okay, so we define the MGF in this sense that will be mxt, the moment generating function of the random variable x. Again, this t, about this t, we are having certain condition that t belong to the real numbers. In the previous one, the s could be some continuous complex number also, but in this one, the t must be some real number only. Okay, moving ahead with this part, so that will be simply expected value of e raised to the power tx. Keeping the discrete case only, it can be defined for all the different distributions, but I'm taking only the discrete case. So if I go for the discrete, it will be summation for all the values of x. You do e raised to the power tx into probability function of x. If we are having the continuous, you can do go for integration x e raised to the power tx probability function of x dx. So that's how we define the moment generating function for any particular random variable. Okay, I hope that makes sense. Moving ahead, again, this is holding some sort of properties that we have to understand. So we are given some properties. Always remember them. So the first property is if MGF exists, there are some cases when the MGF is not existing, because you can see this is some sort of expectation, and sometimes expectation may or may not exist. Okay, so we move ahead. If the MGF exists, it is unique. It is unique. Unique means to say it will be defined uniquely. So that means to say if you are having some x random variable, if you are having another random variable, y random variable. So these are two different random variables. They will be having different MGF. Okay. Again, like if you are given like two different random variables, and if you find that they are having the same MGF, then you will conclude that these two random variables, they are not different. They are same random variable. Okay, so that is the property of uniqueness. If I move ahead and if you move to the second property, then the kth moment can be calculated from the MGF. The kth moment can be calculated from the MGF by differentiating the MGF kth time and using t equal to 0. Okay, so that means to say if you have to find expected value of x raised to the power k, so that will be simply coming out to be you take the mxt, you take a differentiation for the kth time, and you put the t value to be 0. It will give you the kth moment. Okay, we are having the third property. So if you do like if you keep the t to be 0, then if we do mx at the value 0, that will be coming out to be 1. How this is coming out? So again, the same rule follows. You are having summation for all the values of x. You do e raised to the power 0 x probability function of x. So e raised to the power 0, that will be 1. So summation of probability, that will be 1. So you have to memorize these particular properties of the MGF. In the upcoming lectures, like in the module number 3, when we go for like different distributions, in that particular part, we are going to cover different type of properties and technically different type of like how do we find the MGF, the complete derivation, and we have to memorize a lot of MGF for different distributions. Okay, but for now, this is enough. Let's move ahead then. Now we are having the next concept or the third kind of generating function. That will be your characteristic function. Characteristic function. Okay. So for any random variable, the characteristic function, this is defined like some psi x t. Okay. And this will be simply similar to the MGF, and it will be expected value of e raised to the power. In spite of tx, it will be iota tx. Okay, what I'm saying, we are having the characteristic function that will be simply the psi of x at t, that will be expected value of e raised to the power iota tx. Now iota, that is simply some imaginary number or imaginary unit, you can say. So that will be under root of -1. Okay, and in this particular part, again the t belong to the real numbers. So that's how we define the characteristic function. Okay, again the characteristic function, it must be holding some sort of properties. So again, okay, about the MGF and about the characteristic function. So remember, this is very important. A characteristic function always exists. Like sometimes the MGF fail to exist, but the characteristic function, this always exists. Remember this property. Moving ahead. Okay, again, it is unique. That means to say if X and Y are two different distributions, then the characteristic function of X and Y will be different. For different distributions, the characteristic function will be different. That means to say it is holding again the property of like uniqueness. Okay. Again, if you go for the moments, you can try to calculate the moments also. So if I go for the moment calculation, okay, the moments calculation. So in this particular part, if you are given some x random variable, and if you have to find the moments of that particular random variable, you can find the characteristic function. Moving ahead with that part, if you have to find the kth moment, so expected value of x raised to the power k, that will be simply the derivative of this part. So that will be delta for the kth time xt over delta t raised to the power k, and we have to find this particular part at t equal to 0, and there will be one more term that will be iota raised to the power k over k factorial raised to the power -1. So if you apply this rule, then you will be getting the moments of that particular distribution from the characteristic function also. So that's why like the characteristic function, the moment generating functions, these are like very, very important. So you have to memorize them in the upcoming classes maybe, but for now that is enough. Moving ahead, then we are having the last type of generating function that we have to take into consideration. That is your CGF, the cumulant generating function. Cumulant generating function. So what is cumulant generating function? So let's try to have a look on this part. So in this part, again, you are having some random variable. X is some sort of random variable. It can be like a discrete or the continuous. So the cumulant generating function, that is denoted by some kxt. And this is very simple. It is simply you have to take the log of the moment generating function. So you find the MGF, then you take the log of the MGF, then it will be coming up. Okay, so we can simply see like if you go for the properties, then we know the MGF, it may or may not exist. So that means to say the kxt, it may or may not exist. So the properties, you can simply see, we are having the first property that kxt may or may not exist, may or may not exist. Moving ahead, the second property, it also holds the property of uniqueness. Okay, that means to say like if you are given two different the CGFs, then they are belonging to two different distributions. If they are same, then they are coming out from the same distribution. Okay, moving ahead with this part. So you can find, as the name says, cumulant generating function. So you can find the kth cumulant of x by this form. So we are having kth cumulant that will be coming out to be like kx, kth time you get the derivative, keep the t to be 0. So if you take the cumulant generating function, you differentiate it for the kth time, keep the t value to be 0, then you are going to get the kth cumulant for the x random variable. Okay. So remember few properties, that the first cumulant is the mean. So that means to say that is simply the expected value of x. And if you go for the second, The second cumulant is the variance. So that will be coming out to be like variance of x. That is expectation of x square minus expectation of x raised to the power 2. So that's how we cover the different type of generating functions. So in this particular course, like SH201A, we have to go for the basic idea about different generating functions, different generating functions. So we covered like what is a generating function. Then we went over the probability generating function, then the MGF, then the characteristic function, and finally we covered the cumulant generating function. I hope you're able to understand. So stay tuned. Thank you.